biocompatible synthesis and integration of synthetic materials with living tissue. The integration of synthetic materials with living biological systems has transitioned from conceptual speculation to a central objective in modern biomedical science. Advances in bioelectronics have enabled artificial materials to interface with the body's intrinsic electrical and chemical signaling networks, offering therapeutic solutions for neurological and cardiovascular disorders. However, achieving seamless and long-term compatibility between synthetic constructs and dynamic, soft biological tissues remains a significant challenge. Conducting polymers, CPS, have emerged as promising candidates for bioelectronic interfaces due to their combined electrical conductivity, mechanical compliance, and chemical tunability. Conventional approaches typically rely on ex situ fabrication, followed by surgical implantation. These top-down strategies often result in a mechanical mismatch with tissue, limited integration, and progressive performance degradation. To address these limitations, recent research has focused on the in situ synthesis of conducting polymers directly within living organisms, enabling the formation of substrate-free, tissue-conformal electronic interfaces. In this context, a novel strategy has been developed for the in vivo assembly of an n-type conducting polymer, polybenzodifurandione, n-PBDF, using endogenous biological catalysts. This approach exploits the catalytic activity of hemoproteins, such as hemoglobin and myoglobin, naturally present in blood and tissues. Upon administration of the benzodifurandione, BDF, monomer to living systems, these hemoproteins facilitate oxidative polymerization by forming highly reactive ferryl intermediates in the presence of oxygen. The resulting radical-mediated process yields extended polymer chains directly within the biological environment. Subsequent reductive doping, mediated by physiological water and ionic species, for example sodium ions, imparts electrical conductivity to the polymer network. This in situ synthesized n-PBDF exhibits a soft, tissue-like mechanical profile and demonstrates strong near-infrared (NIR) absorption, ionic conductivity, and long-term stability. These properties enable its function as an ultra-soft, substrate-free electrode capable of integrating seamlessly with living tissues. Importantly, the use of endogenous catalytic pathways eliminates the need for exogenous chemical initiators, thereby enhancing biocompatibility and minimizing adverse immune responses. Experimental validation in zebrafish embryos and murine brain models confirmed the feasibility and safety of this approach. In zebrafish, polymer formation was visually and spectroscopically confirmed following monomer injection, with treated embryos exhibiting normal development, behavior, and high survival rates. In mice, localized polymerization within the brain produced stable conductive networks without evidence of inflammation, neurotoxicity, or behavioral abnormalities. Histological and imaging analyses further supported the absence of tissue damage or immune activation. Electrophysiological investigations revealed that n-PBDF interfaces modulate neuronal excitability by influencing ion channel dynamics, particularly those involving sodium and potassium ions. Notably, the polymer enables reversible neuromodulation through NIR light stimulation. Upon irradiation, photothermal and thermoionic effects induce transient electrical changes that suppress neuronal firing with millisecond precision. This reversible inhibition was demonstrated at both cellular and subcellular levels, including in actively behaving animals, where targeted neural modulation produced immediate and measurable behavioral outcomes. Compared to previously explored p-type conducting polymers, which rely on hole transport and often exhibit limited reversibility and potential toxicity, the n-type n-PBDF system offers enhanced control, stability, and safety. The ability to synthesize and actuate the material entirely in vivo represents a transformative advance in the design of bioelectronic interfaces. In conclusion, whole blood-catalyzed polymerization of n-PBDF establishes a new paradigm for the biocompatible integration of synthetic materials with living tissue. This strategy enables the formation of minimally invasive, long-lasting, and functionally dynamic bioelectronic interfaces. By combining endogenous catalytic processes with advanced material properties, this approach opens new avenues for precise, on-demand modulation of biological systems, with significant implications for neuroscience, regenerative medicine, and next-generation therapeutic technologies.